So let's get started and discuss the Earth's seasons. So this diagram it's a little bit like the moon diagram, where when you see it, you might be like, oh my gosh, I've never really thought about how that happened. And one of the big key ideas here is that the seasons are not caused by the sun's distance from Earth. It is not caused by the sun's distance from Earth. In actuality, we are closest to the sun in January. So during northern winter, we are actually closest to the sun in January. What it is caused by is the angle of the sun. So let's first consider just a globe and sunbeams and Elliott. Okay, so I'm going to use my handy dandy circle drawer right here. Let's see if it's actually working today. It's been stuck lately. Okay, so I got my handy dandy circle drawer. I'm going to draw, let's put Earth over here this time. And I want my Earth to be reasonably big. So I will do, let's do this big of an Earth. That's a nice big Earth. Okay. Probably should have been a little lower down because of that, but that's okay. So here we're going to have an imaginary planet. Okay. We'll call it planet Gargantua buttocks. Okay, Gargantua buttocks has no tilt, and is just orbiting its distant star. And we're going to go ahead and we're going to put Elliots all around Gargantua buttock. So we're going to put an Elliott here. We're going to put an Elliott here. Now, once again, remember, down means towards the center of the planet. So we're going to put an Elliott here, and we're going to put an Elliott like this. Okay, so make sure that your Elliots are drawn this way. And now over here, I'm going to go ahead and put our source of our light. This will be our star or the sun. And we're going to have the rays of the sun arriving parallel, right? So parallel to here. Once again, not less than ideal because I didn't line it up. That's okay. Like this, like this, like this, 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 like this. Okay. And let's suppose that this planet has an axis, it has no tilt, and it's perfectly vertical. Okay, so it's vertical, it has no tilt. This is the planet's, we'll call this the North Pole. Make a axis of rotation this way. So I'll label this axis of rotation. Rotation, this being the north and this being the south. Okay? And for each of these Elliots, we're going to label them Elliott A, Elliott B, and Elliott C. Okay? Now, what do these Elliots actually see from these positions? These observer Elliots all the way around the edge of planet Gargantua buttocks. So, this is what Elliott experiences. So first, we're going to have to talk about a type of line in geometry. Okay, and that line is called the tangent. And the tangent, if you imagine a sphere, okay, or a circle, if you lay a straight edge right up against it, okay, that is going to be our tangent. Okay, it's if you draw a radius, it will be perpendicular or form a right angle with our tangent. So we're going to draw a tangent in each one of these. So here is this. We're going to call this a tangent. This is a math object. It's funny, the labs have you do math review for like the numbery part, but not the geometry that we actually end up using. This course uses a good chunk of geometry. So, and the idea of a tangent becomes very important as we go along. Now, why do we care about these tangents? The tangent approximates the flat ground at a given point. So at B, this tangent here approximates the flat ground underneath Elliot B. This tangent right here approximates the flat ground for Elliot A. So let's draw these three Elliots and what they're experiencing. So I'm going to have Elliot A, Elliot B, and Elliot C. Since these are labeled in purple, I'll keep that A, B, C, like that. Draw my little Elliots. Okay, so Elliot B is probably the most intuitive based on our real experience, our real lived experience, or how we imagine our lived experience to be. This Elliot at B is experiencing the sun basically coming straight down on Elliot's head. So this is the sun's rays. And if Elliot wants to look at the sun at B, Elliot looks straight up to see the sun. Now, is that true for Elliot A and Elliot C? No, it's not, right? So Elliot A so all of these Elliots are at noon, okay? Because this is our axis of rotation. This is the edge facing the sun. If you have trouble understanding that this line of latitude is the one facing the sun is at noon, don't be afraid to email me. It's kind of complicated idea. So these are all Elliots at noon. They're at the same time of day. Okay. So Elliot A and Elliot C experience the sun very differently. Elliot looks out in this direction to see the sun. Elliot C looks out in to the horizon to see the sun as well. So when these two Elliots want to look at the sun, put A, straight out like this. And the sun would be in this direction. So sun is over here. Sun is over in this direction for this Elliot down here. But once again, straight out. So here the sun at B is directly overhead. Whereas, what's it called when the sun is straight out in front of you? It's where? So here it's overhead at noon. At A and B, A and C, it's what at noon? What would you say when the sun is out like that? So if you said horizon, that's correct. So the sun is at horizon at noon. Here we have at horizon at noon. Now, the tricky thing here is this situation with planet Gargantua buttocks is basically the situation that we experience during an equinox, okay? Either the fall equinox or the autumnal equinox or the spring equinox. So this actually models the equinox. If this is our axis of rotation, and this right here, let me get a different colored pencil. I am out of colored pencils. We'll go this line this way will be our equator. So where we have the equator, horizontal, basically the sun's rays are running in the same direction as the equator. This is the situation of a fall or spring equinox. Now, down here, this is going to be the diagram of the seasons. Put that in big letters. Diagram of the seasons. On the next page, this is the diagram I want for this next question that's showing up over here, that I want you to redraw this with the tilts. This is the diagram that I want for this next question. So, just redrawn with the tilts slightly different. So, we're going to start off with the sun in the middle. Ooh, and we're going to definitely put this little safety valve on here. This is going to be super not to scale. Keep in mind, this is to give us like a basic idea of how these angles work. This is not to give us a real idea of the real system. And when we look at these simplified systems, there's a great Buddhist analogy for this. And Buddhists say, you know, it's not the moon, it's the finger pointing at the moon. Always keep that in mind for these models. They're not to scale. Don't expand them beyond what we're talking about in that particular subject, because if you do, it's going to get a little confusing. But this is great for understanding the angle of the sun. So we have our sun. We'll talk more about why it's the angry sun later on. And I'm going to draw two Earths. And I want them basically on that same plane. I want them, your ecliptic, to be horizontal, like perfectly horizontal. So this is Earth. And this is Earth 6 months later. Okay. And this straight line in between here, this is that plane. It's actually a circle, but this plane right here is the ecliptic. Okay, and that's going to be becoming important in just a few minutes when we're really trying to understand the relationship between the sun's angles, the angle of the sun's rays, and where it's light or dark. So Earth has a tilt of 23.5 degrees. So You don't have to use a protractor. I am using a protractor because I want to make it super nice and organized. So I am going to do it like this. And I am going to make my axis of rotation. Make sure that you make these different features, different colors, so that when I'm grading it, it makes sense to me. So I'm going to keep consistent and make my axis of rotation this nice teal color. I'm going to make it real big. That helps in several ways. For number one, I can label it here axis of rotation nice and clearly. I can also put my north and my south on it very clearly. So a lot of people, when they put north and south, they're like, oh, north is at the top and south is at the bottom. That's not quite what's really going on here. True north and true south are determined by the axis of rotation. So your north needs to be at the tip of this axis of rotation, and your south needs to be at the tip of this axis of rotation. That North Pole is constantly pointed at a star. Does anybody know what star that is? Now, if you said Polaris or the North Star, that's absolutely correct. The South Pole, as we'll talk about later, is constantly pointed at the Southern Cross. So let's keep on going. We'll do the same thing. Now, this tilt on this Earth is going to be going the same direction. That's really important. So here's the middle. Oop. How do I want to draw this? There we go. So Earth's axis does not wobble back and forth. It's the axis relative to the sun that causes the seasons. So I got that, north, south, label it, axis of rotation. Label things like I'm an idiot. Be like, wow, when Dr. E is grading this, she's going to be dumb. And that's not entirely off base because I have to grade a whole bunch of these really fast. So the clearer you make your diagrams, the more certain we are that we will not accidentally get points deducted. Now the next thing we need to add is our equator. Our equator is at right angles to the axis of rotation. A good way to picture your equator is imagine a circle or like a little cardboard circle with a pencil stuck through it. Okay, so the pencil would be the axis of rotation. It's vertical, it's 90 degrees, and then that circle along the edge, that would be our equator. So we draw this at a right angle here. Right angle means 90 degrees. You can also say perpendicular, however you feel comfortable. So like this. And like this. And notice that the little dotted line indicating the ecliptic in one side is above that equator. I'm going to label it. Assume we're all idiots. Equator. Equator. Like that. Okay. That's going to become important when we're talking about the incident angle of the sun's rays. So, now, next thing we're going to do is we're going to shade the side that's in darkness. Now stop and think, what side of the earth, what do we call that, the side of the earth that's in darkness? What's going on that side of the earth? Dora the Exploring it. Night. Excellent. So, same thing as the grapefruit, okay? We're still always talking about space grapefruit from the last video. It's going to be divided straight in half vertically. So I'm going to draw a vertical line going this way. Goes right through the intersection, right there. See, like that? Whoop. And I'm going to do the same thing over here. Now, there's going to be a little difference between these two because it's going to be on opposite sides that they're shaded in. So over here, this side is night. And over here, this side is night because that's the side facing away from the sun. All right? So label these really clearly. So this is night, and this is night. Okay. And now we're going to finish this off with an explanation. And we're going to draw some of the sun's rays penetrating the earth or hitting the earth this way. I think one of the times it's really good to have like some bright orange or yellow colored pencils. Okay, so finish this off with an explanation. The temperature, okay, the seasons are determined or caused by the angle of the sun's rays. If the sun's more up and down, right? If the what we call the noon sun angle is higher, okay, the sun is more overhead, that is going to lead to it to be warmer, okay? More overhead sunlight, which you saw in some of those Pearson videos, leads to higher temperatures. Because the sun's rays are sometimes focused in the northern hemisphere, it will be summer in the north. If it's focused in the south, it'll be summer in the south. So as we continue on with this, the way we can label this diagram over here, we would say that it is summer solstice in the north, winter in south, and over here it's the opposite. This is the winter solstice in the north, summer in the south. Now, lots of angles. If you need any review on geometry or anything like that, I'm here to help. So don't be afraid to ask for help. And looking forward, this wraps up chapter 2. We're about to head on to the very short video of chapter 3. Can't wait to have you join me.